Hello, myself Anirban Vishwas. Today I am going to explain some miscellaneous topics like functions, tasks, compiler directives, the subject digital circuit design using Verilog. Let's come. So let us see what is a task. A task is like a procedure. It provides the ability to execute common pieces of code from several different places in a description. This common piece of code is written as a task so that it can be called by task call from different places in a design description. The task can contain timing controls, that is delays, and it can call other tasks and function as well. A task can have 0, 1 or more arguments. Values are passed to and from a task through arguments. In addition to input arguments, receive values from a for a task. A task can have other arguments, return values from a task, and in-out arguments as well. A task definition is written within a module declaration. Here is some example. There is an example of a task definition. The inputs and outputs of a task are declared at the beginning of the task. The order of these inputs outputs specify the order to be used in a task call. Here is a similar other example of a task. Task is task call. A task is called or enabled as it is said in Verilog HDL by a task enable statement that specifies the argument values passed to the task and the variables that receive the result. A task enable statement is a procedural statement and can thus appear within an always or an initial statement. The list of arguments must match the order of input, output, and in-out declaration in the task definition. Here is a simple syntax of the task calling. Let us see for the functions. Functions, similar to tasks, also provide the capability to execute common code from different places in a module. The difference from a task is that a function can return only one value. It cannot contain any delays. It's executed in 0 time, and it cannot call any other task. In addition, a function must have at least one input. No output or in-out declarations are allowed in a function. A function may call other functions. Function definition. A function definition can appear everywhere, anywhere in the world in a module declaration. It is the function range, functionality, input declaration, other declaration procedure, state. An input to the function is declared using the input declaration. If no range is specified within the function, then a 1-bit return value is assumed. Here is an example of a function definition. A function call. A function call is a part of an expression. It is of the form. This is the basic form. Let's see an example of a function call. Register max bits -1 to 0. New register, add register. Registration declaration. Register is equal to reverse bit. Function call is in right hand side expression. System tasks and functions. Verilog HDL provides built-in system tasks and system functions. That is, tasks and functions that are predefined in the. These are grouped as follows: display tasks, file I/O task, timescale task, simulation control task, timing check task, PLA modeling task, stochastic modeling task, conversion functions for calls, probabilistic distribution functions. PLA modeling task and stochastic sorry PLA modeling tasks and stochastic modeling tasks are outside the scope of this book. Display tasks. The display tasks are used for displaying and printing information. These display tasks are further characterized into display and write tasks, dropped monitoring, continuous monitoring. This is the basic syntax of the display and write task. Hashtag display LB, hashtag display layout, display write app, write a, dollar write here. The display task prints are specified information to standard output with end of line character, while the write task prints the specified information without an end or line character. Strobe tags. The strobe tags are $strobe, $strobe F, $strobe A, $strobe BO. This system displays the simulation data at the specified time, but at the end of this time step. End of time step implies that all events have been processed for the specified time step. Monitor tasks. The monitor tasks are $monitor, $monitor IOP, $monitor of. These tasks monitor the specified arguments continuously. Whenever there is a change of value in an argument list, the entire argument list is displayed at the end of the timestamp. Here is an example of initial $monitor statement is given and $time statement is given. File IO task. Opening and closing files. A system function $fopen is available for opening of a file. Let us see an example. Integer file pointer is equal to $open file name. The $system function returns an integer value, a pointer to the file. Write out to a file. The display, write, stop, and monitor system tasks have a corresponding counterpart that can be used to write a. These are all the counterparts of the display, write, stop, and a monitor. The first argument for all these tasks is the file pointer. Remaining arguments for the task is a list of pair of format specification followed by an argument list. Reading from a file. There are two system tasks available for reading data from a file. These tasks read data from a text file and load the data into memory. The system tasks are $read map, $read map. Timescale tasks. The system tasks print timescale. Displays the time unit and the time position for the specified module. The $print timescale task with no argument specified prints the time unit and time position for the module that contains this task file. This is the syntax for the print timescale. Here is a simple output of what appears when the task is called. The system task $time format specifies how the $T format specification must report time information. This task is of the format $time format and the statement is given. Simulation control task. The system task $finish makes the simulator exit and return control black to the operating system. System task $stop causes the simulation to suspend. At this stage, interactive commands may be issued to the simulator. This is an example of its use. Initial #500 $stop. After 500 time minutes, the simulation stops. The timing checks. The timing check $setup. Data event reference event reports a timing violation if time of reference event minus time of data event less than limit. Examples of this time scale is given. This is an example, simple example. This is a simple example task call. This is an example of system tasks. The data event is derived from the reference event. It is the reference event with the opposition error. This is an example with Najek, and this is the system task period reference reports a violation if time of data event minus time of reference less than event. The reference event must be an event triggered event. Edge triggered event. The data event is derived from the reference event. It is of the reference event with the same edge. The reference here is another example. The system task is given and the violation statement is also given. The reference event must be an edge triggered event. The system task records a new reference event time before performing the time check. Therefore, if the data event and the reference event both occur at the same simulation time, a violation is reported. The system task $no change reference event, data event, start edge offset and edge offset reports a time violation if the data event occurs during the specified week of the reference event. The reference event must be edge triggered event. For example, $no change, Najak clear present 00 will report a violation if present changes while clear is slow. Each of the above system tasks may optionally have a last argument which is a notifier. A system task updates a notifier when there is a timing violation by changing its value according to the following case statement. This is the following case statement. Simulation timing time functions. The following system functions return the simulation time. $time returns the time as an integer in 64 bits, scale to the time unit of the module that invoked it. $stime returns time in 32 bits. $real time returns time as a real number scale to the time unit of the module that invokes it. Conversion functions. The following system functions are utility functions that convert between number types. $real value converts a real number to an integer by terminating the decimal value. R integer value converts integer to real. $real to bits real value converts a real into 64-bit vector representation of the real number. $bits to real bit value converts a bit pattern into a real number. Probabilistic distribution function. The function $random set returns a random set as a 32-bit signed integer based on the value of the set. The set must be a register, integer, or a time register. Controls the number that the function returns. That is, a different set will generate a different random number. Disable statement. A disable statement is a procedural statement that can only appear within an always or an initial statement. A disable statement can be used to terminate a task or a block, sequential or parallel, before it completes executing all its statements. It is of the form disable task ID, disable block ID. Named events. Consider the following two statements: register ready done. Get the always statement interacting. Initial begin done and the end. Then the always statement is executed. Here another always statement is executed. The two statements in which always statements are needed to ensure that an event is created on ready and done. This always statement is executed on done and this is executed on ready. It appears that of the purpose of ready and done are to act only as handshake signals between the two alloy statements. Verilog HDL provides an alternate mechanism to achieve this using named events. A named event is yet another data type. The two other data types in the language are the register and the net data type. A named event must be declared before it is used. The event declaration declares two named events, ready and done. Having declared a named event, an event can occur and can be created using the event triggered statement. Mixing structure with behavior. The previous chapter we discussed the various forms of modeling. Verilog STL allows all these modeling styles to be combined in a single module. There is a simple statement, the syntax of the module name, the port list, the declaration, input, output, and all the declaration that you can give in the initial statement, get instance statement, module instantaneous statement, UDP instantaneous statement, always statement, continuous statement, and module. There is a simple example of a mixed style description. Hierarchical path name. Every identifier in Verilog HDL has a unique hierarchical path name. This hierarchical path name is formed by using names separated by a period character. A new hierarchy is defined by module instantaneous, task definition, function definition, name block. The complete path of any identifier with the top level module that is not instantiated by anybody else. This path name can be used in any level in the description. Here is an example of a module hierarchy. These hierarchical names allow free data access to any items from any level in the hierarchy. The value can not only be read but can also be updated from any level of the hierarchy. Sharing tasks and functions. One approach to share tasks and functions among different modules is to write the definition of the shared task and function in a text file and then include this in the required module using the backcode include compiler directive. Assume that we have the following function and task function in the file share.h. Function sign plus and function sign minus and function task presently are clear. Here is how the file can be used in a module. the module signed ALU, AP, operation Z, and the input, output, and register parameters are described. Include we have given the include definition, include shared dot h. Then the always statement is executed in the at the last end module. Note that the backward include directive must be present within the module declaration since the task and the function definitions in the file shared.h are not bounded by module declaration. Alternate way to share function and task is to define the shared tasks and function within the module. Value change dump VCD file. A value change dump VCD file contains information about the value changes on specified variables in design. Its main purpose is to provide information for the post-processing tools. $dump file. This system tag specifies the name of the dump file. $dump vars. This system tag specifies the variables whose value changes are to be dumped within the dump file. Dump of this system task causes the dumping tasks to be suspended. Dump on this system task causes all dumping tasks to resume. Dump all. This system task dumps the values of all specified variables at the time it is executed. Dump limit. This system task specifies the maximum size for a VCD file. Dumping stops when the limit is reached. Dump flush. This system task flushes data in the operating system VCD file buffer to be stored in the VCD file. Format of VCD file. The VCD file is an ASCII file. It has the following information: header information, gives date, simulator version, and timescale unit. Node information, definition of a scope and type of variables being dumped. Value changes, actual value changes with time. Absolution times are recorded. This is a VCD file produced, as you can see. Specify block. The delays that we have discussed so far, such as gate delays and net delays, are distributed delays. Delays for path in a module called module path delays can be specified using a specify block. In general, a specify block can be of the following: to declare path between a source and destination, to assign delay of this path, to perform timing checks for the module. Three kinds of module path can be described within a specify block, which are simple path, edge sensitive path, state dependent path. Strengths. In addition to the four basic values in Verilog HDL 0, 1, X, and Z, additional attributes to these values such as drive strength and charge strength can be specified. Drive strength. A drive strength can be specified for the following: a net in a net declaration assignment, output terminal of a primitive gate instance in a continuous assignment. The order of the values is near important. For an instant assignment of value 1, only the following strengths are allowed: supply 1, strong 1, pull 1, weak 1, highs 1. For an assignment of value 0, the following strengths are allowed: supply 0, strong 0, pull 0, weak 0, highs 0. Charge strength. A trideck can optionally have a charge strength specified as well. This charge strength specifies the relative size of the capacitance associated with the net. Some of the following: small, medium, large. The trideck net row has a small capacitance. The rise delay is 5 time units. The fall delay is 4 time units, as we have seen in this example, and the charge decay time is 20 time units. Race condition. If a delay is not used in a continuous assignment or in an always assignment, a race condition can occur due to zero delay. This is because Verilog HDL does not define how events which occur at the same time are ordered for simulation. While communicating information via variables from one alloy statement to another, use non-blocking assignments while assigning to the variables to avoid race conditions. Thank you.